we're talking about waves today. The idea with a wave is that waves are a transfer of energy, not a transfer of an actual object. So the sound coming out of my mouth, it's not that the particles are coming from my mouth and hitting you in the ear. It's the fact that there's compression of air right here, which then bumps into air right there, which then bumps into air right there. And so it's a transfer of energy through something else. Alright? Now, this is mostly the vocab and all you need to know. Identifying the wave. Lambda is how we draw for wavelength. Okay, so wavelength, that's what that is in there, is lambda. Alright? When you measure any distance, all waves have a distance. That is important. Okay? So, the wavelength is the distance between two identical points, wherever it is. So you can measure from here to there, from there to there, from here to there. You can't measure from here to there, though. Okay? Because that's not identical. One's going down, one's going up. So you need to make sure when you measure wavelength that you're finding two identical points. Okay? Somewhere to get the wavelength. And wavelength is very important. Alright? 47.5 hertz. Using that was the lowest deep bass you could hear. Okay? For those of you that say have some subwoofers in the back of your car. Alright? Usually they sell woofers to be about 20 hertz to say 200 hertz. So if you want that deep bass in the back of your car, okay, this range right here, I think it's 45 hertz I calculated, or 50 hertz. A full wavelength of 50 hertz would be 7 meters long. Okay, so a full wavelength, if I had a subwoofer in the back of my car, okay, and I'm about this far from the back of my car, I cannot hear that bass well enough. Okay, so the wavelength of 50 hertz was 7 meters. You're looking at about here. This is how far away I have to be to appreciate the deep bass of coming out of my car. Okay, coming out of those subs. So when you have those cars with those deep subs, has anyone been pulled over for having a car too loud? Okay, police will do that, you know, right? They have decibel readers in certain residential areas where if you drive by, they'll listen to how loud your car is and they can give you a ticket. For some of you, you might actually not think your car is that loud because you're so close to the speaker, you're not actually hearing the sound as well as a police officer on the corner. Alright? Same thing with if you have entertainment center and you have a big, subwoofer to play the bass while you're watching a movie. You might not be able to appreciate it as much as somebody 2 rooms over. Okay, if you live in an apartment complex, you might really annoy your neighbors. Alright, because that bass is going to be about 7 meters away. Okay? So wavelength is really important. Now the higher the frequency, the closer in that wavelength is going to be. So, tweeters can be, pretty close to you as opposed to that deep bass. Okay? Alright, so amplitude also would be measuring from just the midpoint. It's not the whole height, it would be half of it, basically. Alright? Frequency and amplitude, what would we call that if you're in music? Okay, what would frequency also be called? If you have a high frequency sound, you have a high pitch. Good. If you have a high amplitude, what do you have? Loud, high volume. Right? So those are other ways to think of it. Okay, nodes will be these points in the middle that aren't going to move if you have let me show you what a standing wave will look like. Okay. Let's see here. Alright, let's get a standing wave. Standing wave is when you just see the nodes stay in place. Alright, let's see. I think I need to stand up. Alright, so here's a standing wave. You only have one peak or trough. You only have one antinode. Okay, the antinode are the peaks or the troughs. So this would basically be half of the wavelength, because you're only seeing one, okay? You're only seeing one peak or one trough. Now, if I want to get a full wavelength, I'm going to have to double the frequency. Ready? Let's see if I can get it here. Okay? See that node in the middle? The node is the point not moving. The peaks and the troughs are the antinodes. Does that make sense? Okay, let's see if I can triple the frequency. Whoops. Nope. Let me get it. Yeah? I got it? I got it?
It looks good, man.
Okay, good. Thank you. Thank you. All right, there we go. Thank you. You just let go. Alrighty. With all of this, so that's what the nodes are and the antinodes. This formula is going to be important. Whether we're talking about sound or light, you need to know this formula. Velocity is frequency times wavelength. So make sure you write that down. Velocity is frequency times wavelength. Okay? Okay. We're good? Alright. Now, don't copy down all of this, but the idea is this, because I'm going to actually have better pictures in a second. There are two types of waves, and you do want to know these: transverse and longitudinal. Okay? And what I say propagation is perpendicular or propagation is parallel. What I'm saying is the direction of the actual material, the motion of the material, is propagation. Okay, so when I'm doing that, the material is going up and down while I send a wave across. Okay? So, if I want to do a transverse wave, the propagation will be perpendicular to the direction of the wave. So here's a transverse wave. Ready? Want to see it again? So the material goes up and down as the wave travels across. Okay? Now longitudinal means the direction of the material, the material is actually moving in the same direction. So that would be sound. Longitudinal waves would be, I have compression of air here, that bumps into the air there, that bumps into the air there, and so on and so forth. So here would be longitudinal. The material is moving in the same direction as the actual wave. Okay? So here are better pictures of this. You can let go. Okay, we'll pause now. They started thinking about, like, they thought all waves had to have a medium. So when they started to look at light and realized that it does act like a wave, they decided, well, there must be some medium we don't know about. It doesn't need air to travel through. Okay, if you have a jar. If we had money, we'd do this experiment. But if you had a jar, okay, you could have a loudspeaker inside that jar, and you could play it, and you'd be able to hear the music coming through the glass jar. Okay, and you can see it. You turn off, or you hook up a vacuum pump, suck all the air out of it, you will not be able to hear the sound. Okay, with no air, you can't hear sound. You can't hear sound out in space. Right? That's why if you see the sci-fi movies and you hear the laser blasters going off, you know that really can't happen because you can't hear sound. Alright? Light, however, you can still see through that glass jar. Light is a wave. It didn't need a medium. They realized it didn't need air. So they actually made up a medium. They called it luminiferous ether. Okay, you'll hear people talk about it. Oh yeah, it's just flying through the ether. And that's referring back to the idea where they thought light actually needed this stuff, luminiferous ether, to travel through. It had a medium. Okay? Turns out there isn't such a thing. Okay? They proved there was no such thing as luminiferous ether. It's just that electromagnetic waves, such as light, alright, radio waves, X-rays, all those do not require medium. Pause there. The faster sound will travel. Light doesn't care about the temperature. Okay? Light is just going to be 3.0 times 10 to the 8th meters per second. Alright, if you want to put that in perspective, so let's say the temperature of the air is around 20 degrees Celsius. Let's say the velocity of light, for the most part, most times will be around 345 meters per second. So sound will travel 345 of these every second. Alright, that's pretty fast. Light will travel 300 million of these every second. So if you turn a flashlight on, it's going to go after 1 second 300 million of these. That's how fast light travels. Cool, huh? You got it. And they're going to either constructively or destructively interfere. So if two waves are in phase, okay, the antinodes are both on top. If two waves are in phase, they'll add up, be constructive. If they're out of phase, they can actually cancel out or subtract. Now this is actually, all waves do this. Light can do this, sound can do this. In this room, sound's traveling from my mouth and bouncing everywhere. It's going up against the ceiling, against the walls, everywhere. It's traveling directly to your ears, but it's also bouncing off the wall and going to your ears. Alright, so it's coming from every direction. If we had a soundproof room, okay, the floors, the walls, everything was soundproof. And I had a speaker here and a speaker here. Okay, I could walk around the room. I could stand here, and those two speakers might add up and make a louder sound. Okay, it could be twice as loud as one speaker. But if I went somewhere else in the room, I could be at a certain point where the two waves are actually canceling each other out, and I could hear nothing. I could be right in front of the speakers, but the two waves could cancel each other out. Alright? It could have destructive interference. Light can even do this too. Where if you have light going through certain slits, the waves can cancel out and you can have shadows because of it. Alright, so if you have two notes that are frequencies that are just slightly out of tune, let's say I have some points here where the antinodes are in phase, they're going to add up. Okay? Somewhere else, the antinodes are out of phase, they're going to subtract. So when you have two frequencies that are slightly out of tune, what you're going to get is adding up, subtracting out. Alright? Adding up, canceling out. Adding up, canceling out. That's what we call beats. Anyone in music, in choir, orchestra, band, whatever, you have beats. And in fact, you're the band director. If you have to ask the band director, they'll tell you about it. This is what it'll be like. The term something resonates. The idea is that when two objects are traveling or have the same frequency, they can share something. So if let's say I'm in a guitar store and I pluck a string, okay? What can happen is another guitar standing near me, that same string will start to vibrate, okay? Because of resonance. If you have two objects that have the same natural frequency, and one's giving off that frequency, it will cause the other object to vibrate. Okay, have you seen where people sing and shatter a glass? Where what says is not how loud you sing. Okay, it's not that you're just really loud. It has to match the internal frequency. If you pluck a wine glass, you can listen to its natural tone, and a crystal glass will have a more pure tone.
What's the thing you can do where you put your finger in water and then...
Yeah, that's the same thing. It'll get that natural frequency. Yeah. But so if you pluck that wine glass and you hear that tone, if you're able to sing and match that tone, it'll cause the glass to vibrate. Okay, so you can sing all different frequencies as loud as you want and you won't shatter that glass. But if you start to sing at exactly that tone of the wine glass, it'll start to vibrate. And then if you're loud enough and it vibrates enough, then you can shatter the glass. That has to do with resonance. Okay? Just like the guitar string. Now, the Tacoma Narrows Bridge in 1940, it was a bridge that was supposed to be a new modern marvel. It was the latest and greatest suspension bridge. Okay? And so it was in Tacoma, Washington. So they built this bridge, and as the bridge was getting built, they already noticed that in a light breeze, it would start to sway. Okay? And by the time the bridge was opened, it was a sport to drive across the thing because there would be certain times where you couldn't see the other side of the road because you were in the bottom of a wave. Alright? What was happening was as the wind blew through the bridge, just like guitar strings, it created a natural frequency that was matching the natural frequency of the bridge. So it was causing it to sway. Alright? It had resonance. It had the resonant frequency of the bridge. One day there was a stronger wind, and it wasn't like a hurricane, but it was just a strong windy day, and instead of doing this, the bridge did that. Okay? And the bridge ended up collapsing. That day just fell completely apart. I'm going to show you a video in a second. All right, now, there have been rumors about the military designing resonant guns, where instead of shooting you, they fire out a sound, a signal that would match the resonant frequency of your inner bowels. So instead of you wanting to fight, you'd want to find the nearest toilet. Okay? Have we watched South Park? The Brown Note? Okay, that comes from this talk. Now, I don't know if it's completely true, and we have a Mythbusters where they try to do it, and they didn't have much luck, but that's the idea behind resonant guns. Okay? Now, I do know for a fact, though, this next one. Like 12 years ago, I saw an MIT student present this special kind of speaker. And what the speaker did was, it didn't send the sound out at the natural sound frequencies. It sent a sound out through the resonant frequency of air. So what would happen is, if I pointed the speaker at you, any air particles in line with the speaker would start to vibrate. Okay, and as it vibrated, it would reproduce a sound. So he had the speaker connected to like an MP3 player. He'd point at you, and you would hear the sound, and you'd hear the particles vibrating, and it would recreate the sound. So there's like a violin being played. So he'd point the speaker at you, you'd hear the sound. As soon as he turned it away, you could not hear the sound anymore. Okay? So it was like a laser pinpointed sound. Normal sound travels and goes everywhere. And the higher the frequency, the more narrow the scope, but still, sound travels in all directions, bends everywhere. Okay? But what this speaker did was, it was like a laser, how pinpoint accurate it was. So it would point at you, you'd hear the sound. I turn it away a little bit, you can't hear the sound anymore. Okay? And I've heard that they've started selling speakers like this, but what they use this for is for military. This is now, that technology was used to create these new guns called LiDAR. And what it is it's a huge speaker that they can turn up to a really, really high frequency. And if somebody's walking towards them and they don't know who it is, they can first talk to the speaker and say, hey, please stop. If they don't stop, they can play this extremely high decibel sound that would basically make the person sick until they turn away. All right, and again, they wouldn't be able to do that with a regular speaker because it would get everyone. Okay, but because it's so pinpoint accurate, directly on somebody pointing, if they directly point on you is the only time you feel sick, they use that now with military.
There's some whaling ships that have it now.
Yeah, and yeah, exactly. So, because if they see a boat coming up, or or any kind of ship, if they see pirates coming towards them, they can point that at it, and it's non-lethal to try to deter the people.
Yeah, it just makes their ears hurt.
Yep. Okay. All right. So again, that's gonna be shorter because it's a higher frequency. That's a lower note, lower frequency, so it's going to have a longer wavelength. The idea is this. With these formulas, okay?
We have to draw this down? Or
You'll need to know the formula. You'll need to know these formulas.
the formulas, okay, not the pictures.
Well, you go with it. I would say. I don't know. Draw. Do what you want. Okay.
Do what I want.
This wavelet here. If you look at one wave, it goes from peak to valley. Okay? So that is only a half a wave because you want to go from peak to valley back to peak. Alright, so that is half a wavelength. So the length of this pipe right now is equal to half the wavelength. Alright? With a second harmonic, you have peak, valley, peak. So if you get that sound, you would have the full wave. So the length of the pipe here is equal to one wavelength for second harmonic. Okay, third harmonic, the length would be equal to 1.5. Peak, valley, valley. It's 1.5 times a wave. Alright, fourth harmonic, peak, valley, back to peak. That's 2 complete waves. Alright, now with a closed pipe, the only difference between closed pipe and open pipe is with a closed pipe, one end is closed and you need a node. Alright, that's a closed pipe right there. So what I'm measuring, the length of this pipe is 1/4 of the wavelength of the sound right now. So the wavelength of the sound is about that long. Okay, and I'm matching up with the first antinode of it. So I'm starting from a node and just going up to the first antinode. So the length here is 1/4 of a wavelength. Alright, here, from a node to another node, that's half, and then another 1/4, so that's 3/4, and so on and so forth. So instruments obviously have to use this. Okay, with any kind of woodwind or brass is going to have to use this idea of closed and open harmonics. And I'm not sure which ones they are. If a flute or something like that is going to be a closed or open. But that's the idea with it. Okay? Okay. It travels out. When sound comes off of this tuning fork, it's going in all directions. And all the nodes all travel away from each other equidistant, right? Just like that picture there. Those lines of the nodes moving away from each other at all the same speed and all the same direction. Well, what happens if I move? Okay, what if I move here? What's going to happen is, as I walk this direction, the nodes will start getting a little closer together than they should be. Okay? As I walk away, the nodes on the other side are going to be a little bit further away. So what you're going to get when sound moves is that the nodes will get bunched up as you move in one direction and further away, or get further apart on the other direction. So what you'll actually get is a higher pitch and a lower pitch. Okay? So sound, when sound moves, you'll hear a higher frequency or a lower frequency. Here goes higher and lower.
Yeah.
You hear that? Feel like I'm in mass. Okay. Anyways, so that's Doppler effect. That's the same thing as when you hear the cars fly by, the meow, right? That's Doppler effect also. You hear the normal sound of the engine. If you were standing next to the engine or in the car, you hear one frequency. But as a car engine comes towards you, you're going to hear a much higher frequency because it's going much faster. As a car moves away from you, you're going to hear a much lower frequency because it's moving away from you. You're going to have the wavelengths further away. Okay? Fire truck siren as well. Same thing. It's going to come towards you with a higher frequency. It's going to move away with a lower frequency. All right. This is also how radar detectors work. Where the radar detector is going to shoot your car, the radar gun's going to shoot, or not detectors, but radar guns. The radar gun shoots your car. It might be this frequency, but when it bounces off your car and comes back, it's now going to have the frequency. It's going to be bunched together. So all radar guns do to get your velocity is they shoot out one radar frequency, and when it bounces back, they notice the difference in frequency, and they can calculate how fast you're going by the Doppler effect. Okay, and that's how they can figure out how fast you're going. Now there are things that are completely illegal that, you know, people say, oh, I'm going to beat it by sending out all different radio frequencies, and that jams the radar gun. Of course, if they see that all these different frequencies are going around, they just, you know, arrest you for having something illegal. But anyways, but that's the idea. That's what radar does, is it uses Doppler effect to see how the frequency changes when you move. Okay, we'll end it there.